Solving general chemistry problems. Reaction kinetics. Food dyes are commonly large organic molecules that are generally soluble in water. Their molecular structure absorbs light in particular parts of the visible spectrum so that they can impart different colors to whatever they are mixed with. On the other hand, the molecules in bleach solution produce an aggressive oxidant, it's usually either chlorine or oxygen gas, depending upon the type, that can break up the bonds in these organic molecules, change the way they interact with light, and thereby remove their color properties. Here could be two containers of a food dye and water. Watch closely as I simulate the addition of a bleach solution to both of them. Look for the difference in the reaction rate at which the bleach attacks the dye molecules. The two solutions are at two different temperatures. Let's say one is at 25 Celsius and the other is at 50 Celsius. By watching the rate of reaction, can you identify the temperature of each one? Here is the bleach, and here are the reactions. What do you think? I bet it is likely that you guessed that the reaction vessel that became less colored more quickly was the hotter vessel, and you would be right. Chemical reactions occur more quickly as they are heated. We have previously made the point that a reaction's rate constant K is constant as long as the temperature doesn't change. It is apparent from the two containers of dye that K is larger when the temperature increases, and therefore the reaction proceeds more quickly. During the last half of the 19th century and the beginning of the 20th century, scientists tried to understand why this was the case and developed theories to explain what was observed. The hope was to be able to calculate reaction rate constants from first principles and to then understand the molecular origins of reactivity. The goal was to not be restricted to only being able to determine such things experimentally. Now, the early attempts were to simply find a mathematical equation that could at least fit the data. One of the successful scientists at this approach was the Swedish chemist-physicist Svante Arrhenius. He took inspiration from the work of Henry van 't Hoff, who had published this equation that is named after him. Van 't Hoff helped us to understand equilibrium constants in terms of energetic parameters, in particular enthalpy. At this time, Arrhenius was sensing a deep connection between the rates of forward and reverse processes and a reaction's equilibrium position. He was inspired by the form of Van 't Hoff's equation. While a reaction's rate constant was observed to increase rapidly with increasing temperature, Arrhenius found that a graph of the natural logarithm of rate constants against the reciprocal temperature produced a straight line graph. He proposed his now famous equation and interpreted the exponential energy variable E sub A as the minimum additional energy that must be involved in a reaction for it to occur. He called this the activation energy. Take the natural logarithm of both sides and you can see why the graph of ln of k against 1 over t would give a straight line. The Arrhenius equation continues to this day to be the most common approach to calculating and codifying chemical reactivity. It is best viewed now as an empirical relationship, as scientists continue to ask questions such as, well, what is the activation energy, and what is the pre-exponential factor A, and how can we calculate these from first principles? Nevertheless, it finds wide application throughout the chemical sciences and also in biological systems which hint at their underlying foundation in chemical reactions. For example, the chirping of a cricket on a warm summer evening can be used as a thermometer to measure the temperature of that evening. The cold-blooded insect takes on the temperature of the surroundings, and the contractions that allow it to make the chirping sound depends upon chemical reactions, which occur more quickly as the temperature rises. It's also used to analyze and predict the arrival of spring in Japan by determining the progression of the opening of cherry blossom blooms, which start in Kyushu in late March and progresses northward to Hokkaido by mid-May. Blossoming is also a temperature-dependent chemical reaction. Now, here are some problems that apply Arrhenius' equation that you might encounter in general chemistry. 4-methylphenyl acetate reacts with imidazole to form paracresol and N-acetyl-imidazole. This is a second-order reaction. Experiments were performed at several temperatures, and the results reported in the accompanying table. From this data, determine the reaction's activation energy, the value of the pre-exponential factor, and make an estimate of the rate constant if the temperature were raised to 100 degrees Celsius. Now, for interest's sake, here is the line drawing molecular models. But to solve this problem, we really need to focus on the tabular data for the rate constants. Now, recall the linearized form of the Arrhenius equation. We need to be able to plot the natural logarithm of the rate constants against the reciprocal temperature. It is important to remember to use temperature in Kelvin units and not degrees Celsius. It makes a huge difference. So the strategy is to convert the temperature to Kelvin and then take the reciprocal of that temperature and then calculate the natural logarithm of the rate constants. We need to create a graph with 1 over t on the x-axis and ln k on the y-axis. The slope of such a line is minus EA over r and is how we will find the activation energy. The intercept is the logarithm of the pre-exponential factor. It is easiest to plot this graph in Excel or some other spreadsheet program. When you are plotting experimental data, you most commonly want to plot the data points without connecting lines. Then you want to overlay the best line fit to the data. Now we have intentionally converted the data to make for a linear graph, so a linear fit is added to it. Excel can provide the equation of that best fit line, and by comparing it with the standard form of a straight line, y equals mx plus b, we immediately see that for this set of data, the slope is minus 3481.9 Kelvin, and the intercept is 8.5431. By the way, do you get the units involved here? The slope is change in y over change in x, delta y over delta x. The y data is unitless, and we take the natural log of it, while the x data has units of 1 over Kelvin. Hence the slope is in units of Kelvin and the intercept is unitless. We could go into a long discussion of what happens to the molar to the minus 1, seconds to the minus 1, but let's not. K and A have the same units. Things cancel. We just need to remember to keep the same units going into and out of the logarithm. Now, first find the activation energy. Multiply the slope by minus r, the gas constant. The Kelvin cancels, and we end up with 28.95 kilojoules per mole. To find the pre-exponential factor, raise the intercept value to the power of e and get 5131 molar to the minus 1, seconds to the minus 1. To calculate the rate constant at 100 Celsius, we first remember to convert to Kelvin. It's 373 Kelvin. And insert this into the equation that came from the spreadsheet. Now you could also use the exponential form of the Arrhenius equation, but you get the same answer. Plug it in and see. The equation of best fit predicts ln k equals minus 7.9175. We exponentiate that to e, since they're natural logarithms, and get 0.453 molar to the minus 1, seconds to the minus 1 for the rate constant at 100 Celsius. Compare that with the tabular data, and you should be able to see that it fits right in and makes perfect sense. Now here's another question to consider. When you heat cyclopropane, it can isomerize into propene. When done at 470 degrees Celsius, the rate constant is found to be 1.10 times 10 to the minus 4 per second. When performed at 520 degrees Celsius, the measured rate constant is 1.81 times 10 to the minus 3 per second. What is the activation energy for this reaction? Estimate the value of the rate constant when we increase the temperature to 570 degrees Celsius. First off, we need to convert the temperature into Kelvin. Now we could do as with the last problem and draw a graph with these two data points, find the slope and hence the activation energy. But in general chemistry, you will often have exams in which it is not convenient to draw a graph and extract pertinent data. We do want you to be able to do that, but that is more of a homework thing. In an exam setting, that might take too much time. Instead, you are often given a problem such as this with just two data points. Here is a straightforward way to deal with it algebraically rather than graphically, with just two data points. Write out the linearized form of the Arrhenius equation for each of the two temperatures. To be general at this point, we will just choose T1 and T2 along with the rate constants K1 and K2. Now the critical point is not which one is the higher temperature. What's important is that you make sure that K1 goes with T1 and K2 with T2. Subtract the second equation from the first equation. Remember that when you subtract logarithms, it is the same as taking the logarithm of the ratio. Notice how the ln A terms cancel out. We are able to factor out the minus e over a and collect the 1 over t terms. And here is the equation that we can use. Another arithmetic situation to remember is this, that 1 over t2 minus 1 over t1 is not the same as 1 over t2 minus t1. Substitute in the data and solve for the activation energy. This equation requires you to be careful with your arithmetic. Don't take the ratio of the logarithms. You must take the logarithm of the ratio of the rate constants. Make sure that K1 goes with T1, etc. And make sure you take the difference of the reciprocal of the temperatures and not the reciprocal of the difference of the temperatures. Note the units of reciprocal Kelvin for the term in brackets. The minus signs will nicely cancel because an activation energy must always be positive. You will always have to put energy into a system to get it to overcome the activation energy barrier. Solve for EA. Use the gas constant R. You can always convert this to kilojoules per mole in the end. The activation energy for this reaction is 274 kilojoules per mole. We can now use this information to determine an estimate for the reaction rate constant at the still further elevated temperature of 570 degrees Celsius. First of all, convert the new temperature to Kelvin units. Before we substitute into the equation, which information will we use and which equation should we use? Well, we could either use the same equation and solve for K2 at this new temperature, or we could use our results and find a value for A, the pre-exponential factor, and then use the Arrhenius equation. Now in this case, it will be easier to use the same K2 over K1 equation. I will use the data at T equals 470 Celsius for K1. Now here's a common mistake that students make. Watch out for the units of R and EA. It does not matter if you use kilojoules or joules, but the two of them must be in the same units. Kilojoules does not cancel joules. And I will use energy units in joules. Now substitute into the equation. Work through these kinds of questions to make sure you are comfortable with subtracting reciprocals and using logarithms. Note that the two minus signs will cancel each other, and the units of K and reciprocal Kelvin cancel each other out. Exponentiate both sides. Don't forget that we are working in base E here, so don't raise things to the power of 10. The exponent raised to a logarithm is the expression itself. The two operations cancel each other out. Solve for K2. The reaction rate constant at 500 Celsius is 0.0212 seconds to the minus 1. Take a look back at the original data. Does this make sense? Well, it's 50 Kelvin hotter than the K2, which was evaluated to be 1.81 times 10 to the minus 3 per second. And that value was a little more than 10 times higher than the value for K1, which was 50 Kelvin cooler. This value of 2.12 times 10 to the minus 2 per second is a bit more than 10 times greater again. That seems to make sense.